All right, howdy. Let's give this another try. We don't need any of those. What I'd like to talk about today is a paddle wheel. So something that looks a little bit like this. And what it's going to do is it's going to go around in a circle. And at the end, we're going to want to figure out its angular speed, which would be omega. I don't want to look at it right away. First, I'd like to talk a little bit why it's sort of interesting. And so the reason why it's interesting is because there's a famous experiment that people do, and this has to do with something called the mechanical equivalent of heat. And this was done by a guy by the name of James Joule. And you may not know the first name, but you definitely know the last name because, strangely enough, this sort of thing got him units named after him, units of energy. And so, what he basically showed was that mechanical energy and thermodynamic energy are basically the same thing. And you'd call this, and he probably called it work and heat. And the reason why is there was no such thing as energy at the time. So a big process, a big learning process, a big experimental process in the 19th century was sort of trying to pull all the fields of physics together: the mechanics, thermodynamics, electricity, and optics. Okay, and this was basically one way you could do that is by showing that the energy is the same thing. There is a thing that is the same for the different pieces of physics, right? And probably work and energy, work and heat, mechanics and thermodynamics is the most obvious one because they already had heat engines, right? They already had theories of heat engines and about how much work they could do and what the maximum efficiency was and stuff like that. So this is probably the easiest of them to think about. And in this case, basically what's happening is that if you let this block fall to the ground, this thing spin. Now this thing spins, it's in a fluid. What's going to happen? Well, it's going to push the fluid around, right? And it's going to keep pushing the fluid until the block hits the ground here. At that point, that drag that the paddle has been pushing the fluid with will now start slowing the paddle down. The paddle will slow down. It will go at the same speed that the water is turning at. But at that point, the only force on the water is going to be from the sides of the container, and that is going to introduce another drag. It's already there, but it's going to be the only force at that point. It's going to have this force on the container, and that's going to slow the entire mechanical apparatus down. And at that point, this entire part of the system here is going to look exactly like it did before everything started, except all of the little molecules inside of the water will move around, right? They'll move around faster than they were moving around previously because they're hotter, right? And obviously, if you remember, the temperature is just the mean molecular kinetic energy. One way to write that is the internal energy of an object is some number times the number of molecules here times Kb, which is the Boltzmann constant that showed up earlier, times the temperature. And this is just a conversion from temperature to kinetic energy per molecule. This is in Kelvin, and so you multiply these two things together, you get joules per molecule, or molecules aren't really a unit, so that means they're just in joules, which means it's an energy. It's the kinetic energy of a single molecule, the average molecule, the mean molecule Probably not the median molecule. Maybe the median molecule. I don't know. There, and then you just multiply by the number of atoms times this little factor here that has to do with the different ways the object can move. So you get a factor for moving in one dimension, and you double that for 2 dimensions, and you double that for 3 dimensions. And then you have rotations, and you have oscillations and other sort of internal things that can happen if you have like a molecule. And so that shows up in this constant here that I haven't defined. But basically it's saying this is the amount of kinetic energy in that molecule, and this part here is saying the different ways you can partition that energy in that kinetic energy in that molecule, right? So for a monatomic molecule, you can't have any vibrational energy, for example, because there's no way to vibrate because there's nothing to vibrate against. That's all the internal energy, right? So energy and temperature are the same thing. Heat is the thing that changes your temperature. That was Q, right? Work is the thing that changes your mechanical energy, W. So if I can do work and change temperature, then in some sense work and heat are the same thing. All right. So that's what you get from James Joule, and that's why I was thinking about this paddle wheel. I think about it a lot. It's the sort of thing you like to think about at night. And you can do some other things, like you can figure out this connection here between electricity and thermodynamics, right? There's something called Joule heating, Joule again, right? And in that case, your resistor heats up as you put a current through it, right? Not strange. You probably know that. You may have noticed, for example, that there's a big resistor on the range of your oven, and if you put a pot on top of that resistor and on the range, and you put some water in that pot, and then you put a current through that resistor, somehow the water boils, right? So again, you have Joule heating. All these guys are connected. Then these guys are obviously connected because something else that happens in the 19th century, which is called Maxwell's equations. So James Clerk Maxwell, another James, goes in and figures out that electricity and magnetism are the same thing, and optics comes out. Optics comes out. He wasn't even looking at optics, and optics came out. So electromagnetic waves and optics, they just sort of came out. Or electromagnetic waves being light just sort of came out of the unification of electricity and magnetism in Maxwell's equations, which is not in this class. So in this problem, I want to look at that paddle wheel, and I don't want to look at this spinny bit. Well, I want to look at the spinny bit, but I don't want to look at the stuff in here. I don't care about these molecules. So I'm going to get rid of them, right? What I'm going to do instead is I'm just going to put the paddle wheel up here, right? And I use 3 paddles because that's what was in those little light bulbs. You may have seen those little light bulbs that put them out in the light, and then all of a sudden they start turning from the radiation. I used to sell those when I was, when I was a kid. I used to sell those. A kid about 5 years older than you. And then we're going to keep doing the thing with the string, and it's going to go to the end of the table, and off the end of the table we'll have weight, but we're going to pretend there's nothing pushing on it, so when this thing falls, this distance h, what did I say, h here, what's going to happen is this thing is going to be spinning at some speed omega, and we want to figure out what that speed omega is, that angular speed omega. All right. We'll also have these paddles. It's hard to see here, but what we'll have for the paddles are squares, right? So it's S by S. And then if we have this as our dowel or our rod here, then the distance from the center of that dowel, from that axis here, is s over 2. And you'll think about that real quick. That means from here to the center of this paddle is a distance s. So that's the reason why I used s over 2, is so it would be a nice number. So, it's nice to have nice numbers. Unfortunately, I made lots of nice numbers here, and the answer still ends up ugly. And then we're going to say the radius of this guy here is s over 8. And that's going to be so that we can convert omega and v, right? So at the end here, just before this guy hits the ground, he's going to have a speed v. That's going to be important in our calculations. Okay, so is there anything else that I need to talk about there? I think that's all there is to this problem. This weight is going to fall down, and that this thing's going to spin, and we want to figure out how fast it's spinning. Okay, so let's start with our first part, which is sort of deciphering all this writing, this big block of text. It's the first part of the problem solving. Look at all these different things. Oh, I had 2 spots I didn't put them in the right font. Ooh, no. Okay, so I've got a paddle wheel, which is composed of paddles. So we'll start with those. And I have 3 of those. And let's see, they have a mass, m over 3. So each paddle has a mass m over 3. So m is the mass of the paddle wheel itself, not of any one of the paddles. And then they have a side length, s, so it's an s by s square. And then there's this displacement here, which we said was s over 2 to make life easy, at least as easy as something can be, right, in a physics class. Rod, so, or maybe not a rod, let's call it a dowel, but it's too late. I just said that had a radius. And what radius should I give that? S over 8, because I already did. Right? What other things do I know? I know something about the box. It has a mass m and an initial height h. And so that is basically everything I'm given, I think. All right, so last part of describing the problem is figuring out what we want to find. We want to find the angular speed. It says right there, angular speed. Okay, and we usually call that omega. Omega means big O, but that's a lowercase big O. That's a small big O. All right, let's see. Now I need to analyze the problem physically, right? I guess I categorize these a little bit differently. What would I do? Conserve energy. You might guess that I want to conserve energy in this problem as my main concept. And why is that? Because I kept talking about energy for so long at the very beginning. All right, and so we're going to use K initial plus K final. This is not right. K initial plus U initial is equal to K final plus U final. I don't know where that came from. All right, so let's see if I call here, maybe here, this 0, the initial height is 0, then I can call this Z. The distance that it goes down will be Z, which means the potential energy will start at 0 and go down, right? And the potential energy for gravity is U equals mg delta Z, the change in the height, which is going to be minus Z. So since that's our potential energy, that's linear with distance, right? So we get a nice line. Kinetic energy is going to do the same thing. So the speed's going to increase, or the kinetic energy is going to increase linearly. The speed's not going to go that fast, but it's still going to increase as, the square root of z. Yes. Okay, so that looks like a beginning. Why don't we get to the meat? Right, so we need to do our physics here. So we can later on do our math here, right? And the physics is the fun part anyway. This is the part, physics is the part that's like a puzzle. That's the fun part. So we can start with something that has omega in it. Well, the rotational kinetic energy has omega in it. That'd be a good place to start. So why don't we start with rotational kinetic energy, since it has that in there. And we'll just use conservation of energy, right? So we have 1/2. I'm going to call it I3 for the 3 paddles times omega squared. So that's the amount of spinning energy, right? That's the amount of energy that's spinning this guy around. And we were looking for the omega. Is that the only kinetic energy in the system when this guy's spinning? No, because when that guy's spinning, this guy's falling, right? So there's some more kinetic energy. So that's 1/2 m, which we know, times v squared. And we don't know what v is. We're going to have to figure out what v is. Is that the only energy that we have like that? Well, if we come over here, remember we've got a kinetic energy here that's not 0, then we have another negative kinetic energy over here, which is minus mg times the distance it's fallen. And the distance where we care about is at the end, which is the h right there. Right, so we know that one too, so a little box. Okay, so that's enough to go on to the next thing. So that's about it for the energy. We can either do the moment of inertia, which is complicated and mathy, or we can figure out how to get v in terms of something else. Let's start with that. Start with the speed falling down. What's going on there? Well, if you move, some distance dx here, that means that if the string is not slipping, right? If the string is actually pulling this thing, which we assume it is, if this goes to some distance dx, this arc length dx has to change similarly, right? Which means that some d theta there accompanies it. So basically we have s equals theta times r. That's the one we need. Okay, so we have something like that. If you take the derivative of this, that's v, and the derivative of theta is omega. So our definition of angular speed is s dot, which is omega. No, s dot is v. Okay. V, which happens to be what I'm looking for, is equal to theta dot, which is omega, which we found just above here, so it gets a check mark. It's one of these check marks because it's already been targeted, times r, the radius of this guy, which is the only thing I crossed out, which is s over 8. And s we know. Okay, so we're done with 2. We're also done with finding v, and there's nothing extra in this equation, so we can go up to the question mark. Okay, so I need to find I3. And I3, so we're going to find the moment of inertia. There are basically 3 things that we can do with finding the moments of inertia. One, we can, for a compound object like this one, right, we've got 3 of these little paddles, we can add the moments of inertia together. So basically, if we have a bunch of things rotating around the same axis at the same speed, and they'll all be affected by the same forces or torques or whatever, then all we have to do is add up their moments of inertia. So that would be composition. That's one thing we can do, is we can add up the moments of inertia of things we already know. Okay, as long as they're all spinning around the same axis at the same speed and are rigidly connected in some way, and that sort of thing. The next thing is we can use something like the parallel axis theorem or the perpendicular axis theorem to help us transform from one moment of inertia we already know, one that we can look up in a table or something like that, or do an integral for, and transform it into the one we actually want, right? And we'll talk about that pretty soon. And then there's the last one, which would be actually using the definition of the moment of inertia, which means that you'd have to do an integral. Are you scared now? Probably. There's nothing more scary than an integral. All right, so at least you don't have to do them at 8 in the morning anymore. Next thing we have to do is we have to find that I3, and we'll use composition. Right? Remember, composition just means you put things together. So I3 is going to be I plus I plus I. One for this one, one for this one, for this one, and back. And I plus I plus I is 3I. So I3 is 3I, but we don't know what I is. That's tricky. All right, so next we have to use the parallel axis theorem. Okay, and with the parallel axis theorem, let's say you have a box here, or a box there. We know a moment of inertia around its center there, and then we want to rotate it around some distance over here, say distance s over 2 away, right? Well, then the parallel axis theorem says this is going to be equal, the moment of inertia going around here is going to be equal to the moment of inertia of the center of mass, and it's only for the center of mass this works with, plus m times the distance squared, so s squared over 4. Okay, seems pretty clear. Only this is not for us, right? Because we have a distance s from here to here, right? So it's going to be a little bit different. So I'm looking for I. The mass is, or we need ICM, first, which we don't know. I think it's a question mark, so we'll have to find it. Plus m over 3, because this is for one paddle now. We split it. This was for 3 paddles. 3 paddles are 3 times 1 paddle. We're looking for 1 paddle. That's the center of mass plus this displacement part, m over 3 times s squared, because it's distance from here to the center here is s in the problem. If you'll remember, it's s over 2 plus half of one of these side lengths, s, which is s over 2 plus s over 2, which is s. And so this guy we know, this guy we know, this guy we don't know. We found him, we found him. What are we looking for? We're looking for the moment of inertia around the center of mass. So we'll find that with the definition of the moment of inertia, because integrals are good for you. So ICM will then be equal to S, which is going to basically take the place of one integral, because this is the same distance all the way along here. It's completely symmetric, so that's going to be S. One of those integrals would have been S, but we're going to ignore it because we don't need it. We're going to go from S0 to S over 2, because we're now looking at the center of mass, so we're integrating from the axis to the end of the square, axis to the end of the square, axis to the end of the square, and so on. okay, over again. And so that's our integral point there, and that's going to be times sigma, which is the surface mass density. That's if you have a plate or something that's really thin, right? You often pretend like it's a two-dimensional object instead of a three-dimensional object. So its density is going to be the surface mass density times the area of the thing you're looking at. And so in this case, I'm just going to figure out what that is, but that's sigma times x squared dx. And I just did from here to here on that integral. We also have to do the opposite side, because this is going around the center of mass. So we have to do that opposite side as well. So that means I multiply by 2. Okay, then we've got all that. This guy I know. This guy I don't know. I don't know what that sigma is. The x and dx, I don't know what they are, but this is a clue, right? This means x is a dummy variable in this integral. I'm just going to integrate it out. It's going to go away. Okay, and I'll never see it again. So that's a cancel. That goes away. I'm trying not to be naughty. All right, so finally we get a definition of density, right? And that's basically what I was saying over here is the mass. This case is the mass of one paddle. It's one paddle, which means the mass is m over 3. It's not the paddle wheel, which has a mass of m. It's the just one paddle, m over 3. All right, I know what m is. Sigma, it's equal to sigma, which I am looking for, times the area of something like this, which is s squared. It's s times s, right? S times s gives us our whole area there. That's sigma s squared. And bang, we're ready to execute. We've got everything. Found all of the little stupid question marks. We have enough equations, we can play. Now we can always do the thing where we go backwards, but especially for any integrals like that, I like to do those first because they're the hard part. They're the part that's going to trip me up. So you do it first, right? It's like when you eat dinner, somebody gives you some Brussels sprouts and some steak. You eat the Brussels sprouts first, and then you eat the steak because the steak tastes good, and the Brussels sprouts don't. And when you leave the dinner, you want to remember that steak, not the Brussels sprouts. Okay, so we're going to do the integral first. So let's see. That means I'm going to perform 5. I think its number is. And that means I'm going to integrate 2s sigma. Sigma comes out because it's a constant. So I'm just integrating x squared. So if I integrate x squared, that's 1/3 x cubed, evaluated s over 2, which is s over 2 cubed, right? Because I go from square to cube, minus 0 because this is a 0. All right, so that's more or less what my ICM is. Now, I mean, I don't want to scare you with this, but now what I've got here is not what I want, right? Because I don't know sigma, right? That's a question mark over here. So I want to substitute that back in there. So I'll substitute 6 into A. I've used 5, I've used 6, I've used A. And that means ICM. So where I have the sigma, it becomes m over 3s squared. So that means I have the 2 cancels one of those 2, so I have 1/9 times 1/4. Oh, so 1/9 times 1/4 is 1/36. I just put the stuff in there for the m, times what I have left. I have this s left, s squared. Okay, that looks pretty good. So now I have the ICM as a number. I have to come back up in here and do that. So see all, what do I substitute b into 4? Alright, that means I have 1/36 plus 1/3. So I equals 1/36 plus 1/3 ms squared. So that is 1/36 plus 1/3 is 1 plus 12 over 36, which is 13/36 ms squared. I got rid of the 4. All right, and then I want to find I3, the moment of inertia of the whole thing that's spinning. So I substitute c into 3, multiply this whole thing by 3, which is 1312 ms squared. Okay, so that's pretty good. Now, got him. Now this guy needs to go in here, and this guy needs to go in there. So that's probably what we should do, right? No reason to get confused over this entire thing. So E will be the substitution of D and 2 into 1. And that would be a whole lot of math. All right, so that's 1/2 times 13/12 from here times omega squared s squared, m omega squared s squared, plus 1/2 times s over 8 squared, which is 1/64, I think. I hope I'm doing this right. M s squared omega squared is equal to mgh. All right, F. So I'll just combine these guys, I think, I hope. Let's see, so I can, how does 12 relate to 64? Not so well, because it's got a 3 in it, right? So let's see. If I pull 8 out, so we'll have like 1/8, 13 over 4 plus 1 over 64. Is that right? 1/8 times 13 over 4. No, it's not, because I pulled out the 4. That's 16. Okay, so that's, I'm going to have to do this because I can never remember this. 16 times 13 is 208. Okay. That's 13 over 3. Look at me. Okay. Plus 3 is equal to 211. So that means we have 211 over 16 times 3 times 8, which is 384, which is a whole bunch. So that's not a big number. It's a little bit less than 1, but it's still a number-ish number, right? And that's ms squared omega squared equals mgh. I can't tell you how many different times I've redone that and still gotten the same answer, so I really believe it's right, 211 over 348. All right, and G, I'll solve for my favorite omega. So omega, oh, this is almost not enough room, is equal to 384 211ths times G times H over S squared. Okay. Does that make sense? Well, it makes a little bit of sense, but that's our next objective. This should be a capital H here, shouldn't it? Oops. Oh well. So the first thing, symbols. What do we have? We have G. G is a universal constant. It's there. And then we have the H, which goes here, and then we have an S that goes there. And that's what I said before. Good, good. So far I haven't said anything differently. What do I want? I want the units of angular speed, which is angle over time, and angle has no units, so it's just 1 over time. All right. Then I have this guy here, the GH over S squared. That is the units of G times the units of H times the units of S to the minus 2, which is LT to the minus 2. Oh, and this is all to the 1/2. Got to remember that part. That's important. LT to the minus 2 times L to the minus 2 to the 1/2, which is all equal to T to the minus 1. So these guys match. It's okay on that score as well. So the last thing that we have here is to worry about is whether it actually makes sense. Does it make a reasonable amount of sense? Let's look at one thing. What if we increase these dimensions, right? If we look at bigger paddles, does it make sense that bigger paddles would take more energy to speed up, is what we'd be saying, or that the final speed would be less if the paddles were larger? And I'd say that's probably true, right? So if we make these things larger, then it's going to, ceteris paribus and all of that, all other things being equal, then the paddle will take more energy to speed up. And if it takes more energy to speed it up, then the frequency will be slower for the same amount of energy. And the energy is the height. So, yeah, that makes a perfect sense. So we're done with that. We're good. Probably the most important thing to look at is these 3 parts, because we haven't looked at moments of inertia, and we no longer have classes to look at moments of inertia. You have the Walter Lewin videos, obviously, and those are nice, but these are things that people screw up with. These are basically the ways you can do these things. You can find your moment of inertia by adding up the moments of inertia of things that are smaller parts of the whole, right? Through a sort of reductionism. All right. A second thing you could do is you could use a parallel axis theorem using this idea that the moment of inertia, how difficult it is to speed something up, is basically the resistance to motion, angular motion, increases with the distance from the axis from the center of mass. And in a very interesting way, which is that it's the motion of the center of mass. It's the resistance to motion of the center of mass plus the resistance to motion of a particle of the same mass, a point particle of the same mass. That's a distance. That's a distance from the central axis, equivalent to this center-to-center distances that we have previously, and with the same mass as the object. So we have sort of the point particle moment of inertia for the rotation, or the orbital sort of rotation, plus the spinny part, the part around this, the part for a free part of the moment of inertia for a free spinning object. If it's free spinning, it will always spin around its moment of inertia. We can constrain them with things like axles to rotate around other axes. But if something's rotating by itself, it's rotating around its center of mass. So we have these three things that we can look at to do that. We talked about the composition, we talked about the parallel axis, and then we have the integral. This was a fairly simple integral. You might have one, for example, on your web assigned homework. So this center of mass, moment of inertia, could be calculated like this. Normally, what do? We look them up in a table. And so this is your fair warning to put in your notes a big table of moments of inertia. That's perfectly fine. If I don't tell you to calculate the moment of inertia around that center of mass, then I'm probably expecting you to look it up, all right? Because it's a lot of work, you can see, to get that right, as compared to what you're actually using it for. All right. The other interesting thing to note is that the kinetic energy is in two parts. In this case, we've sort of broken them up physically with each other, with this translational part and this rotational part. It's all the same thing. It's all based on how much each atom, each molecule is moving in those extended bodies. But because this is rotating at a constant angular speed, or maybe not a constant, but since all of the things that are spinning around this axis are rotating around at a constant angular speed, using this moment of inertia thing tends to help a little bit more. So this is kind of your spin, and this is your translational, but it will also count as sort of your orbital if you wanted it to. All right. And we'll talk more about that when we talk about physical pendula in a couple of weeks. And look at that. We are done. And I think I've pointed out the important things. Yeah, that's important too. That's important, but it's from week 1. So thank you very much for listening. I had a great time talking to you. All 5 times that I tried to record this, and I hope that you're having a good time and not freaking out too much. I don't know. That's what we're getting from the administration, is that all of the students are really having a hard time. So I hope everything's going well and you're having a pretty good time, and you live somewhere where you can walk down by the river and all those things, rather than be stuck in a small apartment somewhere. So I will talk to you later, and with another one. I'll try to put another one up tomorrow, hopefully tomorrow or the next day or the day after that or sometime. Bye now. Miss it.